If only I was important enough to warrant that. That's great. Thank you. Thank you. Well, welcome to FameLab Talking Astrobiology with NASA. Thank you all for coming. For the few people in the room that don't know who I am, I'm Dr. Mary Wojtek. What's my name? Wojtek. And I didn't even get to have any of the refreshments. I'm the head of the astrobiology program at NASA. Astrobiology, as you know, is the study of the origin and evolution of life on this planet in order to understand where we might find it elsewhere in the universe. Now, tonight, you are going to see 11 finalists that have competed with over 60 other scientists in a number of competitions held around the country, one in Houston, one in Denver, Washington, D.C., and even a competition online. And these are the 11 finalists. These talented scientists have drawn from their own experiences, as well as some training that we provided to them as part of this competition. And what are they going to do? They're going to take 3 minutes only to describe a scientific concept in astrobiology, planetary scientists, or something more general, without using any slides, a task that is indeed difficult for any scientist I've ever met, using only the props that they can carry up onto the stage with them here. What has brought us here tonight is NASA's commitment, as well as the commitment of the scientists in this room, to public enlightenment, that is fostering science literacy, communicating our science and our enthusiasm for the science that we do, because we appreciate the support of the American public, as well as the resources we get from the American taxpayer. No one understood this better and rose to the challenge, as well as Carl Sagan. Some consider him the greatest science communicator in the 20th century. He left a legacy that inspired many youth and individuals to go on into science careers. And I have the opportunity to share with you this evening a recording from his sister, Carrie Sagan Green, who we were delighted to see joined us in Houston for our competition and asked to address our contestants. So we have a recorded message from her that you'll hear now. Thank you.
Hello. I am delighted that you are here, looking forward to hearing the contestants participating in the U.S. Science Communication Competition Finals. The need to explore sits deep within the human psyche. Men and women exploring space is expensive, but the technological benefits and practical advances for us who are earthbound would be many, as we have already seen, and sharing costs with other nations is certainly going in the right direction. Recently, Stephen Hawking celebrated his 70th birthday and commented, "I don't think we will survive another 1,000 years without escaping beyond our fragile planet." I'd like to give you 2 quotes from my brother, Carl Sagan. The first one I have as a bumper sticker on my car. "It is far better to grasp the universe as it really is than to persist in delusion, however satisfying and reassuring." So I implore you to do sound science and not be afraid to give up pet theories if the evidence is elsewhere. My second quote from Carl is this: "If we manage to avoid self-destruction so that there are future historians, our time will be remembered in part because this was when we first set sail for other worlds. In the long run, as we straighten things out down here, there will be more of us up there. There will be robot emissaries and human outposts throughout the solar system. We will become a multi-planet species. I believe that eventually we will be well off planet. Now is the time to increase this investment in our species' future. Regardless if you win this competition or not, always be advocates for science in general and space exploration in particular, and clearly communicate your passion to people everywhere. Good luck to all."
So now I would like to acknowledge our partners, the Cheltenham Science Festivals and the Blue Marble Space Institute for Science, and I'd like to take the opportunity to introduce 2 individuals to you for which if they had not helped me out with this idea, this would have never happened. Sean Domagal-Goldman and Daniela Scalise. Whistling.
I just want to take a moment here to talk about the community of communicators that we've been building through the FameLab astrobiology events. This is AbSciCon, a scientific conference's public communications event. So there's a lot of big brains in the room. But the contestants, not just the finalists you'll see here today, but people that have been participating throughout all our preliminaries, they've done something very brave. They've gotten up on stage and shared their life's work with the public, and that takes guts. And they've done so effectively. They've identified with other human beings with different backgrounds and levels of experience. And the capability to do that also takes heart. And I don't speak for just myself or even just Mary and Danielle when I say that the people that have seen you do that have been inspired by the wonderment and the sense of being that we get when looking at the universe and studying it. And on a personal level, in your attempts to be like one of our mutual idols, Carl Sagan, you've made me feel like another mutual idol of ours, and that's Kermit the Frog. Because we got this stage, we procured a stage, and I twisted some of your arms and dragged you up onto it. But then we got to sit down, and we got to watch you own the stage. And that was very special to us. So I want you all to stand, the 11 finalists, but also all of the people that have participated in any of our Denver. Stand up. Come on, stand up. Stand up and be recognized. Thank you all. I really mean it.
All right. Thank you, Sean. All right. Now, as I think everyone in this room knows, the NASA astrobiology program has always valued and always prioritized training the next generation of astrobiologists. Mary and Sean and I have spent a lot of quality time with some of those young scientists over the last few months, and we're here to tell you that that investment has paid off. We'd like to take this opportunity to say thank you to the senior scientists, advisors, and mentors in the room. Your commitment to them is evident. As you'll see in a moment, the support and guidance you give them every day, day in, day out, in good times and in bad, is reflected in their incredible talent, their boundless energy, and their unwavering commitment to astrobiology. So thank you again, and keep up the good work. Okay, we're going to get started. Without further ado, I'm just going to take one moment now to remind everyone, go ahead and silence your cell phones, please. Okay, I'm going to begin by introducing the judges. They have made a huge contribution to this effort over the last few months, and we're thrilled to have you here again with us. So, David Grinspoon is Curator of Astrobiology at the Denver Museum of Nature and Science and Adjunct Professor of Astrophysical and Planetary Science at the University of Colorado. As you know, he will soon occupy the newly established Baruch S. Blumberg NASA Library of Congress Chair in Astrobiology. David was awarded the 2006 Carl Sagan Medal for Public Communication of Planetary Science by the American Astronomical Society. Please welcome David Grinspoon. All right. Linda Billings. Linda Billings is a research professor at the George Washington University School of Media and Public Affairs in Washington, D.C. She does communication research for NASA's astrobiology program in the Science Mission Directorate. She has advised NASA's lead scientist for Mars exploration and NASA's planetary protection officer on communications. Her research focuses on the rhetoric of science and space exploration and the social construction of scientific authority. Please welcome Linda Billings. Bill Margol has worked for the last 23 years in many positions in the television industry. As writer, producer, editor, developer, and executive, Bill has worked at the Sci-Fi Channel, TNT, the Travel Channel, and Discovery Studios. In 2008, Bill joined National Geographic and is currently Vice President of National Geographic Television. Bill has a love of science and adventure, and in spite of the fact that he would most certainly lose his lunch in his helmet, still dreams of being an astronaut. Please welcome Bill Margol. And I think the moment many of you have been waiting for. We have invited a very special guest to host tonight's event. It seems only appropriate that the Chief Communications Officer of the Starship Enterprise should be part of the inaugural FameLab astrobiology competition. Yes. So here tonight with us is Ms. Nichelle Nichols. When Ms. Nichols was cast by Gene Roddenberry to create Chief Communications Officer Lieutenant Uhura, fourth in command of the Starship Enterprise in his legendary TV series Star Trek, in the words of Dr. Martin Luther King, it became, quote, the first non-stereotypical role portrayed by a black woman in television history. In 1992, she became the first African American to place her handprints and signature in the cement walk at the famous Mann's Chinese Theater, along with her other command crew members of the Starship Enterprise. They were also honored in a special exhibit at the Smithsonian's National Air and Space Museum in Washington, D.C., an unprecedented accolade for the entertainment industry. Ms. Nichols' public service activities have been equally outstanding. Working with NASA in the late 70s, she successfully recruited the first women and minority astronauts for the Space Shuttle program, for which she received NASA's Distinguished Public Service Award. She continues to be a close friend and staunch supporter of Dr. Mae Jemison, who first saw Lieutenant Uhura when she was 9 years old and was determined to follow her dream to become the first woman of color astronaut, which she did. Please join me in welcoming Ms. Nichelle Nichols.
Daniela, thank you.
Pleasure.
I thank you. I thank you so very much, and thank you, Daniela, and thank you, Marion, and this whole organization. And I thank the blessing that brings out so many people who believe in where we're going, where we've been, and how we're going to get to the next step. Doesn't make any difference. We're gonna go. We're gonna go, and we're gonna get there, whatever it takes. Young men and women who are contestants, finalist contestants tonight, you give me shivers. So any mistakes that I make up here are your fault. I think you're the luckiest people on the planet, including those who are not part of, you are part and parcel of this wonderful event tonight. It gives me great pleasure to have been asked to be part of this. And I don't know what I'm doing either, so whatever happens, pretend that I know what I'm doing. I was so honored when NASA asked me to partake. And now that I'm here and see you all, I truly know how important what you're doing, what you're giving, what you're receiving, and what will make this world a better place. Each and every one of you have a hand in this. And so it gives me great pleasure, and I'll get to my business. Thank you, judges, for joining us, our truly auspicious panel of judges. And away we go. Contestants, good luck, and you have my blessings, each and every one of you. You each deserve it. Thank you. Our first contestant here at FameLab Astrobiology, our first contestant is Michael Chafton. Michael Chafton. And even though I lived in the 23rd century, I beam back here now, which means that the perfection that mankind achieved in the 23rd century has not quite caught up in this century, so I'm going to put my glasses on. Our first contestant is Michael Chafton. Chafin. Jeez. Chafin. He's a planetary scientist. He will be addressing the following question. How did they get her up on the stage? No. Does science require faith? Michael?
Are you ready? We're going to resolve all conflicts between science and faith in under 3 minutes. And I'm going to help by telling you a story about the stars. The stars rise in the east and set in the west, passing overhead every night. But one star doesn't move, Polaris, the North Star. We call it Polaris because it's above the Earth's pole. And if you can imagine spinning a basketball on the tip of your finger, it's on one of those 2 points on the basketball that doesn't move as it spins. It doesn't move in the sky, and that's why it's so useful for navigation. But Polaris wasn't always the North Star. The Earth spins like a top, and like a top spinning down, it wobbles. The wobble is so slow that it takes 26,000 years for the Earth to wobble once. That's slow enough that when we point to Polaris, we're pointing to the same North Star that Columbus pointed to. So this wobble, which scientists call precession, is slow. It's hard to detect. So maybe you're saying we've only known about it for 50 years, maybe 100 tops. But I'm here to tell you that we've known about it since antiquity. 2,000 years ago, a man named Hipparchus was an astronomer on the Isle of Rhodes in the Mediterranean Sea. He was the first astronomer to make a comprehensive chart of the stars. He would look at a star in the heavens and mark it down on his chart. And while he was making his charts, he came across an earlier chart, made 200 years before by Timocharis of Alexandria. And he noticed a strange discrepancy. The bright star Spica was 2 degrees off in Timocharis' chart from where Hipparchus saw it in the sky. 2 degrees. If you stretch out both of your thumbs in front of you at arm's length, that's about 2 degrees from end to end. It's a small enough difference that I think most people would have looked at Timocharis' chart and said, no way. The stars don't move, not that much. The heavens are supposed to be perfect, right? Unchanging. But Hipparchus had faith in Timocharis, a man who'd lived 200 years before he was born. Faith that he had made a difficult observation. It's the same kind of faith that we need today as scientists, especially in astrobiology, a field which combines disciplines, combines expertise that takes more than one lifetime to accrue. And on a deeper level, when people say that science and faith are opposites, I think what they mean is that faith is we're content with unexamined explanation, whereas science requires deliberate exploration. But science, in a very real way, does require faith. Faith in each other, but in a deeper way, as Hipparchus knew and as Carl Sagan once said, faith that somewhere out there, something incredible is waiting to be known. Thank you very much.
Michael Chafin. And now we're going to take 3 minutes of questions and comments from our judges. That was wonderful, Michael, incidentally. Thank you very much. Judges?
Michael, that was great. Thank you. So, as I understand it, you're saying that even as scientists, even though sometimes people say science doesn't require faith, it does, because you can't do every experiment yourself and you have to take other people's word for it. So, but then you can't take everybody's word for everything. So how do you distinguish between what you should take on faith and what you shouldn't?
It's a great question. So there is a practical way or a pragmatic way in which science does require faith, right? We can't go out there and repeat every experiment. But at the same time, right, there's a deeper level of faith that's required in science, a faith that our brains, which after all are evolved from single-celled organisms, are capable of understanding and interpreting the universe. I think it's very important, right? Science is not all about faith. Fundamentally, it's about let's see, let's go out there and do experiments and test things about the universe, right? But there's a faith that we're all in that together, that as a scientific community, we can unravel the secrets of the universe and distill them into concrete statements.
Thank you, Michael. That was really a terrific presentation. I particularly like your close, and I have a very quick question and I like a very quick answer because we're limited to 3 minutes.
Sure.
When did you first become aware in your scientific career that you needed to operate on some faith?
Well, I don't know. So I guess it starts out, the way that our education system operates, it's sort of teacher in front of, sage on a stage, right? There's a teacher in front of the room telling you things on faith, right? And sort of I think everybody takes science on faith initially. Maybe the gap that you need to breach is to say, I have faith that I can discover these things myself, that as a community we can go out there and figure things out.
I think you did a great job, and I don't have a question. I have a comment that I think really intrigued me when they said the title of your talk. I immediately said, "Oh, faith. Oh, he's going to be talking about the connection between science and God," and I really was impressed the way you redefined faith and challenged the expectations of what I was expecting. So that was a great job, and I also thought you had a great use of body language. There's something wonderful when you can say it's 2 degrees, and it's a very obvious thing that the audience can appreciate. So great job all around.
Thank you very much.
Thank you, Michael. We'll take 3 minutes of questions. Oh, we already did that, didn't we? Our next contestant is Kate Follett, and she is an astronomer. She's going to tell us that they call it space for a reason.
When I talk to people about what I do, which is to look for planets around other stars, they almost never ask me questions about planets. They want to know about aliens. In fact, no joke, the gentleman sitting next to me on the plane on my way here to Atlanta last week said, "So you're an astronomer. Why haven't you found ET yet?" And I said, you know, I sense this frustration in him and in other people who ask me these questions, and I want people to know that we really are trying. It's not just laziness on our part that means that we haven't found a habitable planet yet. It's fundamentally a problem of space. After all, we call it space for a reason. So I want to do a simple model here to put that into context. So I want you to imagine that this apple represents the entire Earth, everything you know and love. Just kidding. Okay, so if this is the Earth, then the moon would be about the size of a penny, so our nearest object to the Earth. And this is the audience participation part. I'm going to move it away from the apple, and I want you guys to make some noise when you think I've made a good model of the Earth-Moon system. So here I go. Okay, so about here-ish. Of course, I fed them that, but here-ish is where most people guess. But in reality, I can't even stretch my arms out far enough. So I'm going to need to set this apple down and move 6.5 feet this way. So here's my penny. And I'm just going to drop it because the moon is sterile, and there's no life there. So I'm going to keep going. And at this point, I'm farther away from that apple than any human being has ever been from the Earth. And as I reach the edge of the stage here, I'm not even anywhere near Mars, our nearest neighbor. Mars is, in fact, 1/4 of a mile that way. And the edge of our solar system, where the Voyager spacecraft are now, so the farthest any man-made object has ever been from the Earth, that's 4 miles that way on the other side of downtown Atlanta. So when we're looking for planets around other stars, we need to go to the nearest stars. How far away are those? Our nearest star is 140,000 miles that way in this model. That's halfway to the moon, the real moon, okay? And at that distance, what we're doing, we're astronomers on that apple over there, we're looking 140,000 miles away for another apple. And in that context, it seems like an impossible problem. So, I'm here to tell you it's possible. In fact, we've already found at those kinds of distances watermelons and cantaloupes and even grapefruits. We just need a little bit more time to shrink the size of the fruit that we're finding until we find another apple out there in the cosmos and science catches up with science fiction. Thank you.
Judges?
Well, first of all, I'm hungry now.
Would you like it?
Either that or you can pay me the penny. So I'm the guy sitting next to you on the plane when you head home, and you go through and you tell me how big space is. So my question to you is, if space is so big, okay, so how are we going to find ET?
Well, I mean, it's pretty remarkable. The technology that we already have has allowed us, and I was making a joke, but we really have found things that are only a little bit bigger than the apple in this scale model. We've found super-Earths that are a couple times bigger than the apple, which is why I use the grapefruit. So I think given that, there's reason to hope that, technological improvement will continue and we'll be able to find one.
That's great. Thank you.
Very nice job. I really liked your fruit metaphors. And how did you come up with the fruit? Was it because fruit was sitting outside in the lobby all day?
Well, I used to use a tennis ball, but I didn't want to eat that, so.
So you think, so we're going to find these apples pretty soon, but then how are you going to figure out if there are any worms on them?
Luckily, that's not a problem that I have to investigate. I have faith in these guys.
Thank you, Kate. Ooh. Worm in an apple. Hold on. Okay, judges, while they're doing their 3 minutes to judge, the judges have 3 minutes. The judges have 3 minutes. The 3 minutes are up. Our next is Heather Graham. She's an organic geochemist, and she's going to talk about hashtag Occupy the Universe. Hashtag Occupy the Universe.
I have a confession to make to all of you, and this is very unpopular for me to say, but I'm a 1%er. I'm part of the 1% you've heard about. Actually, David is as well, you should know, and strangely enough, so is his hat. But before you raise our taxes, you should probably know that all of you are 1%ers as well. And all the occupiers on Wall Street are 1%ers. In fact, everyone on the planet, including our planet and all the other planets out there, we're all 1%ers. So you're probably wondering what makes us all part of this exclusive group. And it's because we're made of matter. So that means we have volume, we take up space, and we have mass, sometimes more than we'll admit to, and we can be detected visually with the senses. But nearly 99%, most of the universe out there, we can't see, can't be detected visually. But even though we can't see it, we have ways of knowing that the 99% is out there. One of the ways that we know is we look out with telescopes into space, and we see these big hot clouds of gas out there. But they're not acting like a cloud. They're not dispersing. Instead, they're being held together very strongly by gravitational force. And you remember that gravity is the attractive force between two masses. So that means there's some big mass in that cloud that we can't see that's holding it together. So another way that we have of detecting the 99% is we can try to estimate the mass of galaxies. And we do that by using the motion of objects within them. And when we calculate that mass of a galaxy, it's much, much greater than if we were just to count up all the individual masses of the luminous objects in the galaxy, things like stars and dust that are lighting up. So that means there's some big mass in that galaxy contributing to its total weight that's not lighting up. So we call it dark matter. But now that you know that you're all part of the elite 1%, you're probably wondering why we should even care about the 99%. I mean, honestly. But actually, the 99% is pretty important. Without that big mass in that galaxy, it might just fly apart for lack of gravity. And this is going to sound very melodramatic, but actually the fate of the universe depends on the 99%. See, our universe is locked in a struggle right now between the leftover momentum of expansion from the Big Bang and the gravity of all the objects within it that hold it together. And if at any point that gravity becomes bigger than that outward momentum of expansion, our universe will crunch in and collapse on itself. But luckily, some of that 99% out there has this very strange trait we don't really understand yet that's exerting a negative pressure on the universe. So instead of falling in on ourselves, we're expanding at an ever greater rate. So that means for us 1%ers, every day we're not squished by our own universe, we owe it to the 99%.
Judges?
Thank you, Heather. That was a very nicely constructed narrative, and I thank you for that.
Yeah, that was great. But while we have you here, I just have to know, so what is the fate of the universe and how much time do we have?
Oh, I'm not at liberty to say. I'm so sorry.
I thought it was terrific. I think, you know, the thing about the thing that you've done well here is you've taken a construct that we all have heard about, obviously, in the news for the last however many months, and made us all think about it, and, you know, and drawn this great analogy. So really nice job tonight.
I've been desperately afraid that people will forget about the Aquafy movement before this will happen.
No, terrific. Thank you.
Thanks.
Thank you. Thank you, Kate. Our next speaker is Noah Hammond. Noah is a planetary scientist who will speak about the late heavy bombardment, the solar system's civil war. Noah.
The most violent time in the history of the Earth was 4 billion years ago, during what I like to call the solar system's civil war. So it had profound effects for life on Earth and implications for life in the universe. So let's pretend Nichelle Nichols is the sun, or our star. So right next to her, we have the inner solar system. Among them, Earth, fragile, maybe with oceans and life on it at this time. And out here, we have Jupiter and Saturn, the enemies of Earth. So they get into this kind of gravitational tug of war, where as they pass close to one another in their orbits, they attract each other with their immense gravities. And that changes their orbits dramatically. And the asteroid belt right next to it some of it is flung through the inner solar system, attacking the inner planets, bombarding their surfaces. So this is a theory called the late heavy bombardment. And the evidence for it comes from the moon, When astronauts went to the moon, they collected samples from some of the largest impact craters. And we dated those samples to all be around the same age, of 4 billion years ago. So that means if the moon was impacted, the Earth was even more so. Its larger gravity would pull in more impactors. So picture this in your mind's eye. An asteroid so immense that it careens through the atmosphere and boom, impacts the Atlantic Ocean and boils off all the water. This is how extreme we think this event might have been. So it's very likely that life on the surface of the Earth would not have been able to survive this event. But if it lived below the surface, shielded from the chaos above, it might have. And there are organisms which we know can live in that area. A second possibility is that life had to arrive after this event, in which case it did so very quickly, because some of the first chemical evidence of life we find happens just after this solar system civil war. So that means it didn't take as long as we thought to go from atoms and molecules to some of the first living organisms. And if it didn't take long for life to arise on this planet, it might not take long for life to arise on other planets in other parts of the galaxy. So from the solar system civil war, we learned that the probability of life elsewhere might be higher than we thought. Thank you.
Judges?
Nice job, Noah, and encouraging punchline. I like to think of the chances being good out there.
Yeah.
I have a question. So you said that Jupiter is the enemy of Earth, but we often hear about, in astrobiology, about Jupiter protecting the Earth from a greater number of impacts that we would have if Jupiter wasn't fending off the asteroids and comets. So when and why did Jupiter switch sides?
That turncloak, yeah. Well, what we know is that since Jupiter, the largest planet, has a very large effect on comets and asteroids near its orbit. And so at that time, it got into this 2-1 resonance with Saturn, which moved it around. And it exerted its influence on the solar system. And now today, it's in a more stable orbit. And many things are still impacting it, like the Shoemaker-Levy comet that we saw today. When that came out, it's like, oh, thank you, our protector, Jupiter. So the key message is it has a very strong influence on the solar system.
Great job, Noah. Thank you. I have a question. If you were a microbe with a movie camera standing behind a rock 4 billion years ago on early Earth during the late heavy bombardment, what would you see? I mean, are we seeing bombardment every day, every week, every month, every few years? Can you give us just quickly, like a picture of what you would see?
Ooh, that's a tough question. And if we had a time machine, I might like to go back and see that. But I want to take some protective gear. It's difficult to really say. I know that the moon has many very large impact craters on it, and during the time when it was being bombarded, which was over a period of around 200 million years, there was some very humongous impacts. And how far apart they were spaced, I can't exactly say off the top of my head. But it's an excellent question.
I don't know if I could top that question. So, Noah, obviously you've got great skills as a communicator, and there's a lot of great scientists here in the room. Why do you want to not only do science but communicate it? What's so important about it to you?
Well, I think that there's just so many cool stories about the universe that nobody's really heard of before, and telling them is just so much fun. That's the short answer in a nutshell, right there.
Thank you.
Thank you.
Thank you, Noah. We're now going to hear from Lucas Joel. No, did I do that? You were Lucas Joel. It's Lucas Joel. Are you ready? Lucas is a paleontologist. And Lucas is going to explore the curious case of the first animal movement. Lucas.
We all love a good detective story because detectives ask the most intriguing questions. Who did it? Who committed the murder? Who stole the jewels? Paleontologists, which are scientists that study fossils, ask many of the same detective-like questions. How did this animal, which is now a fossil, die? How did it live? One big problem paleontologists face, however, is their fossils, or their crime scenes, have sometimes been left out in the heat and rain for millions and millions of years. This can make mystery solving a little difficult. But what if we could go back in time to the scene of the crime to see these animals as they once were? Well, lucky for us, I'm a time-traveling detective. And we can use my magical time machine to go back and, on this trip, solve one of the greatest fossil mysteries of all time. That is, what was the first animal to ever move? So why waste any time? Let's get going. Back to the Jurassic period, over 150 million years ago. Zwing! Step out, and what do we see? Well, dinosaurs, of course, they're everywhere. Look, there's a massive stegosaurus lumbering along. Dinosaurs all around, all of them moving. But is this the first animal movement? No. Life spans the past 3.5 billion years of the Earth's history. We have to go way back to see the first animal movement. So back into the time machine, an additional 400 million years into the past. Zwing! Step out, and where are we? We're in the Ediacaran period of geologic time. There are no land plants, no land animals, but if we swim out beneath the waves, we see a gorgeous scene, a garden of alien-like life forms that we can see with the naked eye. For the first 3 billion years of the history of life, life was microscopic. You couldn't see it, but now we can see things with the naked eye. First glance, everything we see is stationary. Nothing's moving. But wait, what's that? There's a tiny little worm moving through the sand, pushing aside grains that are almost as big as he is. This is the first animal movement. While small, this worm has huge implications for all life. And that's because this worm is a bilaterian. A bilaterian is an animal with bilateral symmetry up and down the midline, as well as a through-going gut, like you, me, dinosaurs, mosquitoes. What bilaterians also have is a body cavity, and this is the key feature enabling this bilaterian to move through the sand. So really, this little guy is all us bilaterians in one. Remarkable. I'd say that until we discover an even older moving animal, we've solved the mystery of the first animal movement. So now we know some of the earliest animals could move. But what's even more singular is that this worm is part of the dawn of complex life on this planet. So because we've already run this early evolutionary experiment here on Earth, it gives us a framework or a search image for how life might evolve on a distant exoplanet. And life on another planet, well, that sounds to me like a mystery worth solving.
Thank you, Joel. Judges?
Very nice, Lucas, and you know, always great when you can use props to reinforce your case. So you get up and you're talking to a group of sixth graders. Because I mean, science communication, you know, is often about getting them young. Can you maintain that level of energy the whole time, or do you?
I don't know. I'm not as young as I used to be.
Well, excellent, and I particularly like your use of sound effects because I'm convinced that's the exact sound that a time machine would make if you were to go back in time. So very nice.
Great job, Lucas. Thank you. I have two quick questions. Who's your favorite detective? And if you could choose a planet to go on your own mission to look for life there, what would you choose, planet or planetary body?
My favorite detective? Well, I have to pay homage to Sherlock Holmes. I never said his name while I was up here for good reason. But if he had been a scientist, he was a scientist, but if he had been one that in the way we think of it, he would have been a paleontologist.
That was great. This is sort of a nerdy question maybe, but what about the little bacteria with cilia that swim around. Why aren't they the first animal movement?
So this is the first animal movement.
So they're cells, they don't count as animals. Okay.
No.
Gotcha. Thank you. It was. Thank you. Thanks a lot.
Quick answer. Good answer. Our next contestant is on the FameLab stage coming up, astrophysicist Brendan Mullen.
I'll be back.
Brendan wants to know, where are the aliens? Where's Brendan?
I'm right here.
I want to know, Brendan, where are the aliens?
I haven't sold it yet, in case you're wondering. Which is weird because, you know, this is prime real estate here. We're on a planet rich in liquid water and breathable air at just the right distance from the sun. We've got an asteroid belt right in our backyard full of plenty of raw materials for building spaceships or silver jumpsuits or whatever aliens do. It doesn't make sense, you know? Like, I should be swarmed with potential buyers now. Because you know it's not that hard to travel between the stars. Seriously, I mean, we could do it if we really wanted to. In just a few generations' time, ambition, and innovation, we could propel astronauts out of the solar system at 1/10 of the speed of light. And if that were you, now you would be halfway to the moon by the time I finish this sentence. It's fast. In decades, a century of travel, the nearest stars and the planets that orbit around them would be yours, or your descendants, more likely. After settling down for a while, they could send out their own pioneers and reach more distant stars. And over time, waves of our interstellar voyagers would cascade across the fertile worlds of the cosmos. And if we can do that, so could someone else, right? Well, starting from just about anywhere you can see in the night sky, another civilization could leapfrog star to star just like this and wind up on our doorstep after 100 million years, tops. I know what you're thinking. Oh, Brendan, you're far too handsome to wait around that long. You flatterers. No, I wasn't going to plan to wait around that long. Now, they've had plenty of time to show up already. Why our Earth has been around long enough that if aliens arrived every 100 million years, we would have been visited dozens of times by now. No aliens, and no sail for me. No one has set foot anywhere near our solar system, despite what you might have seen on the History Channel. And we can't be the first civilization either, no. Over the last 13 billion years, more stars have formed in our local cosmic neighborhood, the Milky Way, than the total number of people who have ever existed on our planet. Even if just 1/millionth of 1% of those stars have had worlds around them at one point like ours, and could support a civilization like ours, that's still over 1,000 alien species. And it only takes one to conquer the stars. So this should have been easy money. But where is everybody? Thank you.
Thank you, Brendan. That was wonderful. I really like your use of numbers. My head is spinning. But this is an important topic which Kate addressed in a very different way from a different angle, and I thank you for it.
You know, actually, I'd like to hear you explain something, because I think it's an interesting concept that I never quite grasp when everybody talks about, well, where are the aliens? It's the idea that, well, they may be out there, but our timelines may not line up. That, you know, well, how am I describing this? That the civilizations may be millions of years off.
That's true, but if they're millions of years off, they would have time to show up here. Of course, then that raises the problem, like, you know, equivalently, what kind of conversation would we have with ants? You know, so that's one possible solution to this, but I mean, ultimately, from the astrophysical side of things, which is what I study, the universe, ladies and gentlemen, wants to kill you. But luckily for us, it does a really terrible job at it, and it only lobs something terrible at us every 50 or couple 100 million years or so. Things like asteroids, wayward comets, and the occasional gamma ray burst, stellar explosion that beams its radiation in our direction. So the idea here is that, if everyone experiences these things, then we should all be about the same level, and that's one possible solution. So we could all of our civilizations in our galaxy could all just be staring out at the night sky being like, hello, where is everybody,
So what is your favorite answer then to this question?
I would say it's 75% of what I just said about all the universe trying to kill you and all that. And I would throw in a little dash of sustainability with that, because it requires a lot of energy, and I think on the order of a GNP to actually get the resources together to shove some people off into space. So, we like to just look at pictures of cats on the internet all day. Why wouldn't someone else, So.
All right, thank you.
Okay, I'm going to get this one right. Our next speaker is Liz Persack Dennett. Yes?
Yep,
All
perfect.
right.
The Earth is old, really old, 4.5 billion years old. Now, can you guys easily get your head around exactly how long that is? I can't, and I'm a geologist. The thing is, though, by understanding these billions and billions of years, this deep time or geologic time, we get the sense of how the Earth came to be the way it is today, how life has been able to evolve and thrive on this planet. So to demonstrate this, I brought the best prop I could think of. Myself. You see, I'm 5'10" tall. That means if we were to represent the age of the Earth in my height, 1 inch would be 65 million years. That means all the way down here at the soles of my feet, 4.5 billion years ago, the Earth is forming from a planetary nebula. We see the first life on Earth about 1 billion years later, up here beneath my knees. These are single-celled organisms called bacteria, or germs as we know them. And these are what I study. About 1 billion years later, we see a buildup of oxygen on the planet. The oxygen you and I breathe today is thanks to these bacteria. That allowed for more advanced life, things like algae, things called eukaryotes to evolve. And those eukaryotes dominated the planet till my chin. For billions of years, all life on Earth was too small to see with the naked eye. At my chin, as we learned about earlier, you get an explosion of life, things like starfish and worms. At my nose are the earliest ancestors to the dinosaurs, which sadly die out about 1 inch from the top of my head. So where does that leave us as humans? Where do we fit in? Well, using my time scale, our earliest ancestors, which were about 500,000 years ago, they diverged. You can summarize humanity as a single hair on the top of my head. So think about that next time you pull that stray hair off your shirt. That flimsy hair represents all of humanity. And that is why understanding geologic time is so crucial. Because by knowing how the planet came to be the way it did today, how we came to be here, we know what to look for in the universe. And so I leave you with this thought about the universe. It's about 14 billion years old, or in my time scale, 18 feet tall. So I would be standing on the shoulders of a Liz who was standing on the shoulders of another Liz. So if life on Earth began here and gave us humans, what might life look like on a planet where life began 8 feet below my feet?
I like your big sigh of relief there at the end there, Liz. A great comment. One of the things in television that we do is we reinterpret all the time. And I think one of the things you did really well is you took a concept that we've seen demonstrated other times before. Sagan did it famously with the cosmic clock, is that what he called it? You know, and by putting it in the terms of you reinterpreted it for all of us. So it's always nice to see someone take something that's been done before and do it in a really good and new way. So that was great. So thanks a lot.
And I did this because I figured you guys all have the same prop you can use. No, this is key. So when you're sitting on the airplane flying back to wherever you're from, when I head back to Wisconsin, go Badgers, you guys can explain this. And you can say, you know, we humans, we're not everything. We're one hair. I think that's important.
Took the words out of my mouth, Liz. I was going to compliment you on the use of a prop we all have. I have the big chart on my wall to show, you know, geologic time, but using your body as your ruler is much more meaningful, I think. Thank you very much.
Yeah, that was really great. So how much higher above your head do you think life on Earth might be able to go?
I would love to have another Liz standing on my shoulders. I think that it's a really good thing to keep into account, though. And there was some talk earlier just about sustainability and how we're doing this. And by understanding that we're that hair, it really gives us a sense of what it might take to even see us survive another inch on top of my head. I guess we will find out, huh?
Great. Thank you.
Thank you, Liz. Wow. I get to a second chance at this one because I mispronounced her name before. Aomawa. Aomawa Shields is an astronomer, and she's going to deliver a presentation entitled Bipolar Ice. You go, girl.
14 years ago, I left a career in astronomy because I thought there was only one way to be a scientist. There was only one kind of person who could be a scientist, and it wasn't me. Today, I know there is not only one way to be a scientist. Just like as a researcher, I've discovered that ice doesn't behave in only one way. Say there's a planet orbiting the sun with some bright white ice at the poles. Most of the sun's light is light that we can see with our eyes, visible light. Ice on that planet is going to act like this white shirt and reflect most of the visible light that hits it. If that ice could talk, it would say something like this to the sun's visible light. Okay, thanks, but like, no thanks. Like, light is energy, and energy can heat. So, like, I'm gonna take a little of your light and give you the rest back. Like, I don't wanna melt, I wanna grow. And the more light that ice reflects back to space, the less light it absorbs. The colder the planet gets, the more ice forms. My research has shown that without any greenhouse gases in the atmosphere to keep the planet warm, planets around stars that are even brighter than the sun could become ice-covered, snowballs. But see, here's the thing. Ice doesn't treat all types of light equally. It doesn't behave in only one way. Let's take stars that are cooler than the sun. Most of their light is infrared light, not visible light. Ice on a planet orbiting a much cooler star is going to act like these black pants towards infrared light. If that ice could talk, it would say something a little different to its star's infrared light. It would say, "Come on in, baby. I want you. I need you. I have to have you. Don't worry, baby. I'm not going to reject you and reflect you. I'm going to absorb you. That's how much I love you." And the more light that ice absorbs, the warmer that planet gets. Remember, light is energy, and energy heats. The warmer that planet gets, what's going to happen to that ice? It's going to melt. So what this means is that we may not see much in the way of ice on planets orbiting cooler stars. And smaller, cooler stars are most of the stars in the universe. So our planet, with its bright polar caps, could be pretty rare. But as I've found in my life, there are many ways to be a scientist, so there are likely many ways to make a life-sustaining planet, ice or no ice. In science and in life, there are always many possible ways. Thank you.
Judges?
That was great. I think we're seeing a theme here of people using props that they don't have to carry onto stage.
Exactly.
Yeah.
So much easier in the suitcase.
Yeah. So that was a really neat way to illustrate your point. I have a question about the planets around those red dwarf stars. Wouldn't they just, or wouldn't those stars just have planets farther out that had ice, farther away from the stars?
So yes, if you get farther in, so I'm assuming that all of these planets are at the distance from their star where they receive the same amount of flux from their star that Earth receives from the sun. So we're putting them all at the place where they're in their habitable zone, where liquid water could exist. But yes, if you kick a planet far enough away so that that flux is way, way less, then you could make ice anywhere.
That was a lovely job, Aomoa. Thank you very much. And I wanted to compliment you and take the opportunity also to compliment everyone thus far, and I'm sure those who follow you will do the same, to use your body as a prop and to invite us all onto the stage with you and get us to listen to your talk about science by just inviting us to look at you and look at how comfortable you are and how much fun you are. And all of you have done this, and you've done it really well. I've seen all of you before, if not live, at least in recording. And it's so important in communication. It's a way of establishing a relationship with your audience. So you've done really well there.
Thank you.
Okay, am I the only one in the room who really wants some ice now? No, it was terrific. So question for you. Back at the beginning, you said you left science for 14 years. What brought you back?
I fell in love with astronomy again. I was tired of learning about the astronomy breakthroughs on TV with everyone else. And so I went away and I studied acting and was like pulling staples out of paper for a living and thought, you know, I think I have a planetary science degree. I could probably get a better job than that. So I actually got a job at Caltech working for the Spitzer Space Telescope, just as a help desk operator, answering questions about the Spitzer Space Telescope. And then I started to go to science talks again and found that I was really attracted to talks about extrasolar planets. And I would go to more and more talks and get more and more interested, and so my interest got reignited. And I thought, you know, I became willing to go back and get that PhD and stay this time.
Well, congratulations. That's great. Thank you so much.
Welcome back. Wow. Whew. So much. Everybody, you're so great, all of you. And here comes another one, so great. Rebecca Turk-McLeod, to the stage, please. She's a molecular biologist, and she's going to tell you about the RNA world. Rebecca?
How did life begin? No, seriously, does anybody know? I don't know the answer to that question, but it's something I'm really interested in, and I do have some ideas about what I think might have happened. And I think it's based on very simple principles and very basic chemical compounds. The problem is that life is so complex. It's hard to imagine how it could have come about because it's so complex. Cells are very complex. They're made up of all these different bits and pieces, right? There's DNA, which is so important. It's the instruction manual for the cell. It makes it so the cells can replicate and you can make more cells, so that's very important. On the other hand, we have proteins. Proteins are the workhorses of the cell. They catalyze reactions, which just means that they make things happen more quickly than they would if they were just floating around. Now, wouldn't it be cool if there was one kind of molecule that could do both those things? And it turns out there is, and it's called RNA. And RNA, as you might guess from its name, is kind of similar to DNA. It's kind of like this piece of paper, actually, because it contains information. But it also does something really cool, in that it folds itself and forms structures, like this little bunny rabbit. And these structures can carry out functions. Functions like catalyzing reactions. Now, I'm not trying to say that RNA is a bunny rabbit or the first life looked like a bunny rabbit. What I'm trying to say is that now that we know this, it's not that hard to envision an RNA world in which all of the functions of life were carried out by one kind of molecule, not all kinds, all different kinds of molecules. And if we can envision that happening on Earth, maybe that has happened, maybe it is happening on other worlds right now. Thank you.
Thank you, Rebecca. That was really good. And I particularly appreciate your prop to illustrate that structure can perform function. That was very nice. I appreciate it.
So it's a really cool idea about the origin of life. How could you test it?
Well, we have done a lot of work to test what are the capabilities of RNA, what kinds of reactions can it catalyze. And actually something that I've worked on is how did the first proteins then come about, after that happened, because obviously we needed proteins. And it turns out that RNA can actually do all of the reactions that are necessary to form proteins all by itself in kind of different bits. And what I'd actually really like to do someday is have kind of an RNA party in a test tube and see if we can actually start making proteins just with RNA.
I think I don't have anything to add. I think that was really terrific. I love anytime somebody can do origami on stage. It's all good. Great job.
Wow. I'm glad Uhura took up communications. Thank you so much. Okay, I'm going to try this. Parag Vasham Payung. Yeah? Hot dang. Parag studies planetary protection. After all that's been on there, I think we're going to need some. Planetary protection. He's going to come up and talk about the true nature of self. Parag.
We as a human being take an extreme pride in ourselves as highly evolved and intelligent species on this planet. But I want to find out what is the true nature of self, because all our research, our understanding, our findings are centric to this self-identity or our self. To find out that, we have to take a small journey, a very short journey, to the end of this known universe. And we're going to borrow the spaceship from Michelle. Can we? And then we'll start our journey with the speed of light, and we're going to start moving from this own planet. Within 5 hours and 15 minutes will be the end of our last planet on this Pluto. Sorry, Pluto is not anymore a planet, right? Damn. We'll get over it, Mr. Tyson. That's fine. We're not going to stop there anyway. We'll continue our journey perpendicular and keep moving. All the stars disappear and keep moving. Within 5,000 years, we cross the closest sun, Alpha Centauri, to our solar system. But we're not going to stop there too. We'll keep moving, and it's not till 100,000 light years we pass, and we can see the spiral structure of our own galaxy, our Milky Way. We're not going to stop there either. If we keep moving, every moving star is no more a star. It's an entire galaxy comprised of billions and billions of stars within it, and more complex and diverse than each other. 1 billion years, 5 billion years, and after 10 billion years, we will stop and we'll look back where we started. And when I look back, I could see the extreme tapestry of this known cosmos. If I look back and I feel small and short, there is something wrong with me. I don't feel like that. Because every carbon, nitrogen, and oxygen in my body was born somewhere out there in those distant galaxies, and it's within me. I feel great. Hindus call it as Advaita, or non-duality. Some call it as singularity, and some call it as cosmic kinship. Carl Sagan understood that, and that's why he said, "We are star stuff." And if we understand this true nature of self, we can do a lot of good discoveries. And this is why I want to pass this message and leave you with this thought. But tonight, when you go to bed, at least think once, what is true nature of self? Thank you.
Judges.
That was really lovely and inspiring, and I liked how you worked the phrase billions and billions into it. Yeah.
Thank you, Parag. That was lovely. And I think it's an important concept for us to discuss, particularly with our non-experts in our communities, that we are all a part of the universe. We all live in the universe. The universe are us.
You made me feel so much better tonight. You know, I think one of the things that you've done is something that other people have done here, and you've each done it in a really unique way, which is to express scale in a very different way. You know, one did it through height, you've done it through speed. I think that's admirable, because I think one of the things, especially laymen like myself, fail to understand often is scope of science. And I think you did a great job of that. I have to ask you, because we have a little bit of time left, something that has nothing to do with your talk, but has everything to do with what you study, which is planetary protection, which is just the coolest thing in the world. So what's the thing that planetary protection people worry about the most?
Sure. So planetary protection has two things to worry about. One is forward contamination. That means you don't want to carry any bugs with you on the spacecraft to other planets, and you don't want to bring any bugs back, which we haven't done yet, but we don't want to bring anything back from other planets to our own planet. So we make sure that we are not carrying microbes with us on the other planet. Being said that, we cannot completely sterilize the spacecraft, but we make sure that it's below a certain threshold that it's not going to contaminate the other planets.
I feel safer now, so thank you.
Thank you. Thank you, Carol. So I'm star stuff. I like that. Where do we go from here? Is that the end? One more. Uh-huh. I guess I'll put my eyeglasses on. I knew you were there all the time. Just teasing you. Finally, we're going to see Nicole Younger Halpern. Nicole Younger Halpern. She's a physicist, and she's going to deliver a presentation entitled, "I love the smell of evolution in the morning. It smells like physics."
Life is like a garbage dump. Never mind what you hear about boxes of chocolates. Living systems are organized like dumps. By thinking about a dump, we can understand why life can evolve, why we can exist. Picture a dump. See the rusty bicycles, breathe in the stench of rotting eggs. give our dump a stench rating. If the old meatloaf mixes with car oil, the smell knocks us out and has a rating of 10. If food occupies one bin, metals another, and so on, the smell just turns us pale green and has a rating of 1. Now, picture a primordial soup. Carbon atoms mix with hydrogen, oxygen, and other atoms. Carbon atoms are like milk cartons. Hydrogen is like hamster droppings. The primordial soup is like a dump where the trash mixes. Primordial soups have high stench ratings. Stench doesn't sound scientific. Physicists say entropy. Primordial soups have high entropy. They're disordered. Organisms have low entropy. The atoms in us are organized into molecules and cells. A cell is like a bin in the dump. Dumps that have bins have low stench ratings. Organisms that have cells have low entropy. How can a high entropy, disordered primordial soup evolve into a low entropy, ordered organism? A physical law says that many systems become more disordered. I mean, if we throw more trash in the dump, the smell won't improve, right? Wrong. If we put clothespins on our noses and organize the dump, we can organize the dump only if we dirty our clothes, if we pollute while driving to the dump, if we create more disorder outside the dump than order in it. Similarly, as life has evolved on Earth, the Earth has radiated. We've polluted outer space with energy. Evolution creates more disorder outside living systems than order in them. Evolution can enable organized life to form. We can exist. And life is like a garbage dump. We smell, but we smell like Darwinian victory.
Judges?
Nicole, I remember seeing you in DC and wondering how you can keep up such energy. It's amazing, and especially given the fact it's not easy to go last. So it's really, it's great. And I think one of the things you've done really well is you've painted a picture, a visual, or I guess this time an olfactory picture in all of our heads. And I think a great science communicator, a great communicator, has to be able to paint a great picture and drag the audience along. So great job on that.
Thank you, Nicole. That was wonderful. And when you're rich and famous, your signature perfume will be called Darwinian Victory. And I'm going to take this opportunity because we won't have an opportunity to speak with all the contestants once we go into our chambers. But I've seen you all either live or recorded, and you've all gotten better. You've all gained more confidence. You all came into this competition with a lot of confidence. It takes a lot of confidence to get up there in front of strangers and do your thing. You've gotten better at it. You're more comfortable. And all of you who competed and have not gone up on stage tonight, I'm sure you're all getting better. And the learning curve has been wonderful to observe. So thank you all.
I completely agree with what Linda said. You're all just so wonderful. You have all blown us away, and your energy is terrific, especially in a large room like this. It's just wonderful. You fill the hall. Quick question, since I'm the one with the annoying nerdy questions, because the fact that that you're saying stuff with high entropy is stinky. And I feel like there's something really profound there, but I'm not sure why. Why do high entropy things smell?
Okay. Just to be certain, the smell is part of the analogy. I'm not saying that we smell. I trust you used deodorant this morning. What I'm trying to say is that many physicists like to explain entropy in terms of disorder. Something that is a high entropy system is like a disordered garbage dump. And just like a disordered garbage dump has a high stench rating, a high entropy organic system has high entropy. A sort of disordered organic system has high entropy. So I'm saying that the stench is like the entropy, not exactly the same thing. Thank you. Whew.
I didn't know that I was so complex and beautiful until I heard all of you. And now I'm going home on a high energy level. I thank you all. You're just incredible. Judges, you've got your work cut out for you, and I don't envy you. Yeah, actually I do. That ends the competition, and the judges are going to retire to commiserate. Sean?
Yeah. So I know what you're all thinking. You're all thinking that they have a really tough job to do, right?
How about a big hand for our guys?
A hand for the judges.
Judges, thank you.
So you might be thinking that they've got a really tough job, but you've got the same job. There are note cards that we left on your chairs when you came in and little golf pencils. You got to vote. Okay, we're going to do a People's Choice Award for one of these 11 contestants. So fill them out, hand them to the aisles. We're going to have volunteers come and collect them. And while you're doing that, I'm going to invite up the Director of Development for the Cheltenham Science Festivals, Stephen Burgess. And Steve is going to talk to you a little bit about the history of FameLab. So please welcome Steve to the stage and continue to vote on your favorite choice.
Can we do this, ladies and gentlemen, before you leave? Can we get our contestants to stand and turn around? Because each one of them are winners.
All right, but you can only pick one.
Well, thank you, Sean. Well, while you're all making your hard choices, I'll give you a little bit of a history of FameLab. But first, I would like to thank Sean and the other teams at NASA. Without their incredible energy and commitment, we would have never got this far in such a short amount of time. To put something together in less than 6 months, having been through many FameLab competitions elsewhere in the world, is remarkable. And it is down really to the energy of the three that's allowed us to do this. FameLab was started in the UK in 2005, so it's not exactly out of the primordial soup in here, relatively young. And it was started for one reason only at that point, and that was to find new talent to feed into the Cheltenham Science Festival. Which was a venture of the Cheltenham Festivals group, which produces jazz, music, literature, and science. Sometimes a strange combination in our primordial soup of having science in an arts organization. But in the end, arts and science is all part of culture. And I think the more that we actually get the two sets of disciplines working together, I think the better we'll all be at communicating. So FameLab was basically set up as a talent pool, a pipeline, if you like, to feed into the Science Festival, knowing that there was a shortage of top communicators, even in the UK, where we do have a history of science communication for that. What soon became apparent is we'd actually sort of touched a bit of a nerve with FameLab, and it soon got to be noticed elsewhere. So it was a case of sort of light the blue touch paper and stand well back, and we were somewhat surprised at the explosion of interest in operating FameLab. On a global basis, we couldn't have done it without the support of the British Council, who are a part government organization who operate in many, many countries around the world. They helped us take the FameLab competition in from an infrastructure perspective. Like we have with NASA here, it's very, very important that we have people on the ground who are committed, who can actually work with the local groups to put these competitions on. And now it's running from Israel to Hong Kong, from Lithuania and Poland down to South Africa, and of course with NASA, and a small group in Switzerland called CERN. I'm not exactly sure what they do, but we're also very proud to be able to work with them. So FameLab basically is the future of science communication in many areas. A lot of countries that we work in, they've never really done science communication. It's always been the professors talking to the people and not listening to the people and no dialogue with them. So for us, it's all about public engagement. It's getting organizations and individuals to take science seriously, and the fact that people aren't stupid. They know when the truth is being told. You just have to explain it in creative ways. And these guys today have done a fantastic job. I've learned a lot. I've seen a lot of FameLab competitions over the last couple of years, and they're a very, very talented group. So FameLab really is breaking borders. It's going to go into many more countries over the next couple of years, hopefully into India, into China, in Brazil. In India, it'll be an interesting one, being a competition-driven country. I think letting FameLab off in there will be very, very interesting. So again, many, many thanks. We appreciate all your help and interest, and I'll hand you back to Sean, and we'll finish off the rest, and of course the main act. And me being on the same stage as Nichelle, that is just it.
Thank you. So we have one more speaker this evening, and she is going to not be limited to 3 minutes. Please join me in re-welcoming Miss Nichelle Nichols to the stage.
Thank you very much. Thank you, Sean. Wow. I don't know what to say after all of this, but I know that my brain is filled with the magic that you have brought to science and the communication, the manner to communicate so brilliantly, so immediately. I want to thank you, each and every one of you. When I decided what I wanted to be, I was a very, very young girl. And I always wanted to be everything. Music was my life. Dance, I knew that I had to. I went to ballet and then to Afro-Cuban and modern and all forms. And acting was just a natural thing with me. And I see that with you, that what possesses you is a natural part of you. It's just wonderful to behold. And I think then of myself and my wonderful career, the ups and the downs and the in-betweens and the sideways and the great blowouts have all added to who I am. They all add to who you are. And I give thanks to every up and down moment of my life, because it has been a long and varied life. And I'd like to double it. And I don't say that facetiously. I don't think that it's impossible, because we've come such a long ways from 40 to 60 being old. We're no longer old anymore. We're building, we're doing things that we don't have time to grow old. We've got too much to do, and you've proven that. It's just amazing. I always knew what I wanted to do, as I said, and I was doing it. And I was invited, and I've traveled all over the world, well, maybe not all over the world, but pretty much. And I had been in London, and I had decided I had never seen Paris. And I'd been to London several times, but I always had to get back right away. Now I had nothing to do, really, that was going to keep me. And I went to Gay Paris, and when I got there and met friends there, I said, this is the beginning of my home. This is where I'm going to be for the rest of my life. This is where I'm going to express myself, until I got a phone call from my agent. And he said, come home, they're doing Star Trek. I didn't know what a Star Trek was. I said, I'm not coming home. I'm sending for my son and my little son, and I'm going to live in Europe, and he says, come home, they're doing Star Trek. And he thought I knew what Star Trek was, but I really didn't. And the thing was, Gene Roddenberry, 3 years before Star Trek, had given me my first guest star billing in a show that he had called The Lieutenant with Gary Lockwood. And I thought I was on my way, and then nothing happened. And my work was always in Europe, and I loved it, and I was not coming home. And then he made me an offer I couldn't refuse. He said, there'll be a first-class round-trip ticket on Air France or wherever you want it. You come here and go to this interview, and if you don't get it, you can be back in Europe in less than a week, and the ticket is on me. I went, I can go home and get my son and bring him back, and it won't cost me anything. But I didn't agree very fast, and he said, deal? I said, okay, deal. Well, in the meantime, having lived in Europe for some time, enough to say this is where I want to be, I had glamorized myself and become very European, don't you know? I had cut my hair, and I wore it in a natural. And I wore it short in the back. And I had straight sideburns and a pointed bang and a high natural. And someone had taken me to where I could get designer clothes for a lot less than a job's made for. And when I came back, I went into them thusly, with my Dior suit on and my hairdo. I walked into the office where other girls were seating, waiting to go in. And they looked up at me, and they're reading the scripts, and they looked up at me, and they went, and they looked at each other, and they went, because you see actors going out for a role, God forbid anybody thinks they really, really, really need this role, so we usually go out in slacks or jeans and a sweater, and we're really ran into just to read this one for you. And here I am walking in like it's important. And I always read I read a lot, but I always read a big book. I carry a big book, especially if I'm flying across the waters to another country. And I was reading this one book, which was a bestseller, and I was about a quarter of the book through. And I came in with the book, And they took me in front of the other girls who were there because I told them that I had another engagement. Which really isn't done if you're serious about getting the role. They would have told you, well, go ahead and, you know, when you find time, come in. They said, oh, of course, Miss Nichols. And I thought, that felt good. So I walked in with this big book, and they took a look at me and went, five guys, a producer, the director, the cameraman, and so forth and so on. And they looked up at me and they looked at each other and they said, they almost got up, you know, hello, Miss Nichols. Oh, come sit down. And so I sat down and I thanked them, you know. And they looked at my hair, and they looked at my suit, and they looked at my leather shoes and bag to match. My wife has that book. She just bought it. She's raving over it. Another one said, yes, I have. I've just bought it. I just haven't gotten a chance to open it. Everybody knew about the book. So we talked about the book. And they queried me about the book. And 25 minutes later, they said, maybe we should find out what Miss Nichols has come here for. Would you please read? Oh, I'd be delighted to. There was a character of Bones, Kirk, and somebody named Spock. And they said, and it was a wonderful, long, 3-page long scene. And so they said, would you mind reading the role of Spock? I said, I don't mind reading any one of them. They're wonderful in my mind. And so I read and I said, okay. I'm looked through and through and through, and they said, take your time. And I said, tell me something about this character, Spock. What is she like? And they all looked at each other, and they said, don't you know anything about this show we're doing? And I said, no, I've been in Europe. And they said, oh, well, the first pilot didn't sell, and we're redoing the pilot, and we've decided to put a new character in, the communications officer. I said, oh, Spock is a communications officer. He said, no, 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 no. Spock is not a female. It's a male? Yeah. I said, oh, pity. Could it be a female? And they said, well, yes, but Leonard Nimoy would not like it. Ah, a name. So I said, well, why don't you tell me can I pretend it is a female? I can, if you tell me the characteristics of the character, I'll utilize those and give you this character, and you'll know if I can act and if you really want me or not for the role. And they said, fair enough. So they told me how this character was, had an austere characteristic, all the things that you now know of that character. And somebody said he has green blood and pointed ears. I said, well, I can't do green blood and pointed ears, but I can do the characteristics. And so I read for the character. And I went through one page, and they had me keep going, whoever was reading the other characters. And I went to the second day. Well, they took me all the way through. And I said, wow, they don't usually do that, you see, as you know. And so they said, thank you, Miss Nichols, for coming in. And so I said, thank you. And they said, and the director said, and Miss Nichols, would you wait? Oh, that is such a good sign. It means that you're in contention with someone else, that you're up for it. It's not, don't call us, we'll call you. And so I came out, and all the girls were sitting there going, it only took me about 5 minutes to read the thing, but the rest was on this book. So Penny took, the secretary took me into a little anteroom and said, would you wait? So I went and I picked out my book and I curled up on the sofa and I was reading my book, and the director, about an hour later, peeked his head in and said, he's looking for someone. He said, what are you doing still here? Well, I've got a paid ticket back to Europe. And I said, you told me to wait. He said, oh, didn't anybody tell you? I'm picking my stuff up. I said, it's quite all right. He says, no, you had it when you walked in the door. Come on, let's go to lunch. And then I got a call for, well, I don't have to pay now I've got to pay my agent back because I've got the role. And of course, it's the best payback I ever did. But now I get a call for fitting. And so I go in for a fitting, and the designer comes in, and he said, by the way, Gene Roddenberry called down. He knows you're having a fitting. He wants you to come to his office. So I go to his office after the fitting, and he said, with my book, and he said, it's about that book. I said, yes. He said, come on, let's go have lunch. And we went to lunch, Marigold's, and we went to lunch, and there was not very many people there. So he said, well, let's celebrate, and he bought me a bottle of champagne to celebrate my getting the role. And so he said, by the way, I never told anybody that I knew you or had, if they didn't know you had a role 3 years ago, you got it on your own. And I was delighted. So he said, I want to talk about that book. He said, it's something about the character, the name of that book, that I'd like to use for your character, but it's a little bit too harsh. And the name of the book was Uhuru, which was a beautiful treatise on Africa, and which I had explained to all the guys in the room what it was about, and they were fascinated. And he said, but I'd like to. So I picked up my champagne now that I have a job. And I'm sipping it, and I said, well, why don't you do an alliteration on the word and soften the end of it? Instead of an uhuru, put an A on the end of it, uhura. Gene said, that's it. That's exactly what I want. Now I know where you're from. You're from the United States of Africa. Your parents are part of Starfleet Command. You've had a whole background, and he just went on and he was so delighted. And I got nervous. And actually, that is the way Uhura got her name and the way I got the role. It tells you that you really never know in life, with all that you know and all that you've done or not done, what's going to happen with all that you know. And for all the times that I went out on interviews and didn't get them all those years, suddenly every experience in my life took fire and allowed me to create this wonderful character. I don't call it me, I call it her, because she is another character in my life. And all that you know will be the same. You can never undo what you know. You can misuse it and do something else. But what you have, no one can take away from you. And it will enrich your life as Uhura has enriched mine for many years to come. I bless you each and every one of you. I'm just stunned by not only your knowledge, but how you've absorbed it, how you've presented us with an insight. I can feel you, each and every one of you. I can feel how you feel, how you've taken that knowledge and made it part of your life, of who you are. And so today I want to tell you that each and every one of you are winners because you proved it on this stage today. And sometimes we only get one chance to prove who we are. But who you really are, what you own that, and can never be taken away from you. And what you've given us, the insight of how you think about who you are, I'll never forget it. And you'll never forget it, because you got to demonstrate it. You probably even yet don't realize the jewel that you just received today, to stand on stage and open yourself up, each in such diverse and unique ways. And those of you who are still in the audience who were up for this, and anyone within my sight, we have jewels within us that we don't even realize yet. You have knowledge that sometimes you think, well, it's what I do. It pays my bills. Or I'm glad to be a scientist, or I'm glad to be working, I'm glad to be a secretary. Each thing that you do affects another being. And as it affects another being, something grows from there. How I, being grand and came and created that role, did something. And I had many firsts come out of it. The first interracial kiss. The first black actress to have a starring role on a TV series. There are so many firsts. And one of the wondrous firsts was my relationship with NASA. I came to be asked by NASA at NASA headquarters to come and assist them, come on board and assist them. I said, in recruiting the first women and minority astronauts for the Space Shuttle program. All that I'm telling you led me up to that. And in that, it led me here and to many other relationships with NASA. So I don't just play or created or play an astronaut. I found astronauts, and I found NASA. And whenever NASA asks me to come and be part of, I know it's another star in the sky, another first. I get to be here with you, and this is another wondrous, wonderful, and I thank you all, moment in my life. And thank you all for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 magnificent Brendan? Something's wrong.
Here. How many do I get? There we go. That one, there we go. All right, so this pretty much concludes our evening's activities. Michelle and I want to thank all 11 contestants and the other 60 that are here that competed in all of our competitions. We have one winner that we named tonight that as a prize, we are sending them to the Cheltenham Science Festival this summer to compete in the international competition. And in addition, the gift from NASA is we've invited the winner, Brendan, and a guest to join us at JPL in Pasadena, California, to witness the landing of the MSL rover in August 2012. So.
And I'll probably see you there.
I was just going to say that we haven't, you don't get the keys to the rover, but you get to watch it land. So we've selected a single winner, but we really believe that everybody is a winner. And we say that and we honestly believe it. We really do. We are committed to utilizing their talents to further communicate our science. This is the finals for Astrobiology 2012 FameLab. But it is actually the beginning of what we hope these people will do, and we hope that there'll be continued support for their activities. So please give them, all of you guys stand up again, give a final round of applause. I'll let you do it. So just a couple more things. First of all, again, I want to thank our partners, the Cheltenham Science Festival and the, Blue Marble Space Science Institute, or Institute of Science, sorry. Excuse me, Sanjoy. As well as the host of our preliminaries, so the Denver Museum of Natural Sciences, the Lunar Planetary Institute, and the National Geographic. So we'd like to thank them. And some final words to all of you out there.
Everybody raise their hand. Live long and prosper. Thank you.
Space, final frontier.
So as we listen to that,